In a different video, I showed how to perform a meta-analysis when some of the studies report data for two or more independent subgroups. For example, these might be studies that compare the outcome for treated versus control, and they report the data separately for males and females. In this case, we're dealing with independent subgroups because subjects will either be included in the subgroup of males or females, but not both. In this video, I'm going to deal with a situation where studies report data for multiple outcomes or multiple time points, and these are based on the same subjects. So, for example, we might have studies that assess the impact of an intervention on math scores and also on reading scores, but the math scores and the reading scores all come from the same students. Or we might have an intervention that where we compare treated versus control, and then we follow up the patients over time. So we have an assessment at 3 months and we have another one at 6 months, but it's based on the same patients. This is fundamentally different than the case of independent subgroups, because in this case the reading and math outcomes are going to be correlated with each other, or the outcome at 3 months and 6 months are going to be correlated with each other, and we need to take account of that in the analysis. I'm going to use an example here that deals with multiple outcomes, but the situation is exactly the same for multiple time points, so this video can be used for either case. Later, I'm going to deal with a situation where we have multiple comparisons, where we have, let's say, a placebo group, which is used as the comparator for two or more treatments. That situation is similar to this, but different enough, I think, that it warrants its own video. The first thing we need to do is to set up a file in CMA, so I'm going to say insert column for study names, insert column for outcome names, and then insert column for effect size data. Now, probably in most cases what you're going to be entering over here are things like means and standard deviations for each group, or perhaps the number of events and non-events in each group. But just to keep this as focused as possible, I'm going to enter the hedges G and its variance. We'll call these groups treated and control. So over here for the study name, I'm going to use the same data that I used in the example for independent subgroups, so that if anybody's looking at both videos, you'll be able to see how the structure is the same, but the analysis turns out to be different. The outcome, we'll use reading. Sorry, let's use math for the first one, and reading for the second. And then I want to put in 5 studies like this, so I'm going to say insert study, and we'll call the next one study B. Notice that I've checked this box over here that says add a row for every outcome, so when I add study B, the program gives me math and reading for that. Then I'm going to have study C, study D, and study E. So I've got my 5 studies. Then for the first one, I'm going to use effect sizes of 0.3 and 0.1. For the next one, I've got effect sizes of 0.2 and 0.1, 0.4 and 0.2, 0.2 and 0.1, 0.4 and 0.3. And up here for the variance, I've got 0.05 and 0.05. There is no need that these variances have to be the same. I'm doing it that way because it's going to make some of the examples a little bit easier. 0.02, 0.05 and 0.05, 0.01 and 0.01, and finally 0.06 and 0.06. And the last thing we need to do is to give this the direction of the effect. I'm going to call that automatic, which means that if this is a positive effect, it's going to show up as positive, and if it's negative, it's going to show up as negative. So I've got automatic for each of them. Over here I have a column for the standardized mean difference, which we're not going to be using, so I'm going to click Customize. I'm going to get rid of the standardized mean difference. I'm going to get rid of the difference in means. I'm going to click OK. And at this point we have our database. The last thing I can do over here is I can click this button. The program is then going to simply merge those lines. It doesn't have any impact at all on the analysis. It does make this a little bit easier to see, especially if you have more than 2 outcomes, and there really is no limit to the number that you can have. I'm going to save this and call it Outcomes. And at this point we're ready to start the analysis. If I click Run Analysis, I get this analysis over here, which is based only on math. I'm going to right click over there, select by outcome. I can, first of all, I can choose to run an analysis on math alone, or I can choose to run an analysis on reading alone, and either one of those is going to be completely valid on its own. The issue that we need to deal with is what happens if we want to use both math and reading in the same analysis, and the problem is that these two are not providing independent information. If we were to select this button over here that says use all of the outcomes assuming independence, we would actually get 10 rows of data, but the precision of this estimate really is not correct, because this assumes that every row is providing an independent set of information, and since these are based on the same set of students for math and reading, that is probably not true. What we do instead is we say select by outcome, and what I'm going to do is to say use the mean of the selected outcomes, and when I do that, the program computes a mean for math and reading for each of the studies. So for example, for the first study, where the values were 0.3 and 0.1, I get a mean of 0.2, and the variance is 0.05. Now this is where this situation of math and reading is very different from the situation where we had independent subgroups such as males and females. If we come back here and look at the variance for math is 0.05, the variance for reading is 0.05. When we were dealing with males and females, the variance was 0.05, the variance was 0.05, and the variance for the combined mean was 0.025. Since we had twice as much information, the variance was cut in half. By contrast, over here, we're going to treat these two items as though they are fully correlated with each other. Therefore, the second one is not adding any independent information. So if the variance for one is 0.05 and the variance for the second is 0.05, the variance for the combined effect is still going to be 0.05. We have no additional precision. And that's why when we come back here, we see the variance is still 0.05. And then what the program does is it basically performs a meta-analysis on all of these using these variances, which give weights, and we get an overall effect of 0.185 with a variance of 0.005, a standard error of 0.07, and this z-value and this p-value. Now, if the key number then is the variance down here, it's 0.005. If we had assumed that these things were fully independent of each other, which we can do over there, although as I said it's not a very good idea, the variance is not going to be 0.005, it's going to be 0.002. In other words, the variance is going to be cut in half. These numbers are being rounded to 3 decimals, and that's why it doesn't appear to be exactly half. Let me go to increase the number of decimals. So what we have over here is 0024, and what we have with the when we're using the mean is 0.0048. So you can see it's exactly doubling when we do it assuming a correlation of 1. Now, basically the program is forcing you to either assume a correlation of 1, which we're doing over here, or to assume a correlation of 0, which we're doing when we treat them as independent. At the moment, those are the only 2 options that are available in CMA, although we will be adding a much more sophisticated version of this in the near future. But let me show you in Excel. First, I want to go to Excel and show you exactly what it was we did over here. And then I want to show you how you can actually use Excel to do some modifications to the data, then bring them back into CMA. And that will allow you to use a correlation any place between 0 and 1. Let's take a look now at the same data in Excel. I have a column over here for study names, for outcomes, for the effect size, and for the variance, and this of course is the same data that we saw in CMA. To compute the weight for each outcome, I would have the weight is equal to 1 divided by the variance. The effect size times the weight is equal to the effect size times the weight. I copy this information down to the other 9 outcomes. I sum the weights. I sum the column of ES times the weight. The overall mean is equal to the effect sizes divided by the weights. The variance is equal to 1 divided by the sum of the weights. The standard error is the square root of the variance. The z-value is the mean divided by the standard error. And this p-value is a function that is built into Excel. This shows the version for 2010 Excel. If you're using an earlier version, there's a comparable function that will do that. So this is these are the summary values that we would get if we were treating all of these as independent of each other. If it were the case that the math scores and the reading scores were based on a separate set of students. But since they're not, since the information for math and reading overlaps somewhat, the information is not independent, and this variance over here, this standard error, overestimates the precision of this estimate. The correct standard error should be larger, and I'm going to show you now how you would go and compute that. What we need to do is to compute a composite score for each study, the way we do that is not the same as we did when we were working with independent subgroups. Over there we use the meta-analysis to combine the data for males and females. What we're going to be doing over here is different. We're simply going to, first of all, for the effect size, we're simply going to take the mean of math and reading. So that's going to be equal to the effect size for math plus the effect size for reading divided by 2. Obviously, if we had 3 outcomes, we would be dividing by 3. Then, in order to compute the variance properly, we're going to need the correlation between math and reading. I'm initially going to set that to 0. And then the variance is a formula, which I'm simply going to copy over here now rather than type it in. And the formula is shown up here. We explain in the book where this formula comes from. It would be difficult to explain. It would take a long time, and I don't want to spend too much time on that right now. But the key thing is that if you click on the formula, you'll see the formula actually includes in here the correlation. So that if we change the correlation, the variance is going to change. The correlation at the moment is 0, and in the formula it's included up here as J4. And then we can do the same thing for the other studies. So we get that here, 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 and here. And then we have, at this point we have 5 composite scores. We want to compute the weight for each one is equal to 1 divided by the variance. The effect size times the weight is the effect size times the weight. I can copy this for all of the studies. And then finally, to do the meta-analysis, we simply need to sum these values. We sum these values, and then the overall effect is going to be this divided by this. The variance is going to be 1 over the sum of the weights. The standard error is going to be the square root of the variance. The z-value is going to be the mean divided by the standard error, and the p-value again is a function that is built into Excel. Now, what you might have noticed is that at this point, the sum of the weights here is the same as the sum of the weights here. this column, the sum of this is the same as the sum of this. So it follows that the mean, variance, and everything else is going to be the same for this and this. And the reason for that is that we assumed a correlation of 0 between math and reading. And I did it this way to show that if the correlation is 0, then basically what we have over here is precisely what we had before when we were dealing with multiple independent outcomes. If the correlation is 0, then math and reading are actually independent. And the point that I'm trying to make is that what we've done over here by combining the 10 rows into 5 rows and then doing a meta-analysis on the 5 rows, if the two outcomes are actually independent, then we're going to have as much information in the composites as we had in the original 10 rows, and therefore doing the analysis this way is going to give us exactly the same answer as we got doing the analysis this way. With that established, we can move on and see what happens if we change the correlation. And what's going to happen is that the weights are going to get smaller. The amount of information captured by math and reading together is not going to be the sum of 20 and 20. It's going to be something less than that. It then follows that the sum of the weights is going to be less than 413, and therefore the precision of the estimate is going to be the estimate is going to be less precise than it was before. If we were using this with real data, I would leave this set up so that we could set the correlation between math and reading separately for each study, because we might have reason to believe that in study A the correlation is 0.5, in study B it's 0.7, or whatever those numbers might be. But for the purposes of this video, I'd like to be able to change all of the correlations at the same time, and therefore what I'm going to do is I'm going to link each of these correlations over here to this cell down here, and all that I've done now is if I change the correlation in this cell, all of these are going to change. Now notice when the correlation is 0, let's take a look at the first study, the variance was 0.025. If I change the correlation to 1, the variance, instead of 0.05, it is 0.05. The variance is twice as large, because as the correlation between math and reading goes from 0 to 1, we're saying when it's 0 that the information provided by math and reading is completely independent. When it's 1, we're saying that it's completely dependent. So if we have if the information provided by reading is exactly the same as the information being provided by math, we basically have no additional information being provided by the reading, and therefore adding reading doesn't add any information. It doesn't add any precision to our estimate, and that's why the variance is going to be 0.05. Similarly, for the second study, when the correlation was 0, the variance of the composite was 0.01. If we change that correlation to 1, that variance becomes 0.02. Now, the thing we wanted to do after we have these composites is we're going to use a meta-analysis to synthesize the result over these 5 studies. If the variance over here was 0.025, then the weight, the amount of information being provided by this study, was 40. When we change the correlation to 1, the weight, the amount of information being provided by the study, goes from 40 to 20. There's half as much information being provided. And the same thing happens for all of the other studies. And for study 2, the weight goes from 100. When the correlation is 1, that becomes 50. So obviously, over the sum of the 5 weights, when the correlation was 0, the sum of the weights was 413. If the correlation is 1, that cut precisely in half. The sum of the weights is now 206. And whereas the variance before, with a correlation of 0, the variance of the mean had been 0.002, when the correlation is 1, that variance now becomes 0.004 or 0.0048. So basically what's happening is as the correlation goes from 0 to 1, the variance doubles. The thing is, however, that we don't, in general, we're not going to assume that the correlation is either 0 or 1. Let's say, for the sake of argument, that the correlation between math and reading for all of these studies is 0.5. So we can put a value of 0.5 in there, and then the variance for each of these falls someplace between the two extremes. The weight falls someplace between the two extremes. And down here at the bottom, the mean again is 0.185, but the variance now, rather than being 0.0024 at one extreme or 0.0048 at the other, is 0.0036, which is exactly in the middle. So we get a standard error based on that. We get a z-value based on that, and the p-value for the composite, if we're asking if this overall mean is significantly different from 0, the p-value is now 0.002. So this, what we've done over here is we've computed composites where the variance in each case takes into account how much overlap there is in the information between math and reading. And therefore, this estimate down here, this estimate of the variance, standard error, z-value, and p-value is correct, assuming that that correlation is correct, and these estimates over here are all correct. Now let's see how this compares with the information that we got from CMA. In CMA, we were able to tell the program to treat math and reading as though they are independent of each other. When we did that, the effect size was 0.185 and the variance was 0.0024. Similarly, over here, if we set the correlation as 0, which means that these are independent, the mean is 185 and the variance is 0.0024. The other option in CMA was to tell it that we want to use the mean of these, in which case CMA treats the math and reading as though the correlation between them is 1.0. Similarly, over here, if we set the correlation at 1, the effect size is 0.185 in both cases, and the variance is 0.048 here, and it's 0.048 here. So you can see that they're doing the same thing. There is obviously a limitation in CMA at the moment, although we are hoping to change that in the near future, which is that you can say that the correlation between math and reading is either 0 on the one hand or 1 on the other. And it is much more likely in most cases that the correlation is going to be someplace in the middle. So I'm going to show you how you can work around this limitation until we come out with the next version of CMA. Let's say that we come back over here and we want to set the correlation at some value other than 1 or 0. Let's say for the first study it's 0.5, and for the second study it's 0.7, and for the next one it's 0.2, and this is 0.4, and this is 0.8. So what we get now is, for each study, the variance is computed correctly, the weight is computed correctly, and these numbers down here are accurate based on the correlations that we've given for each of the studies. We get an overall variance of 0.0036. Let me show you how you could use this information and transfer it over to CMA to complete the analysis over there. So what we can do over here is we're going to come back to CMA. We're going to start a new file, say insert column for study names, insert column for effect size data, and we're going to use hedges G and the variance. We're going to call the studies, we need now only one line for each one, A, B, C, D, and E. The hedges G values are going to be 0.2, 0.15, 0.30, 0.15, and 0.35. The variance we're going to pick up from here, 0.038. And as a matter of fact, let me just make sure that I'm getting these to as many decimal places as I can. So let's format the cells to show, I just want to make sure that these numbers are going to match exactly. So that's the first one is 0.0375, 0.017, 0.03, 0.007, 0.54. The effect direction is going to be automatic. And then when we go to run the analysis, we now get an overall mean of 0.186, an overall variance of 0.004, and if I show that to an additional place, the variance is 0.0036, the same as we had over here, and the z-value is 0.3110, and the p-value, the same as it was over here, is 0.001868. So the point is that you can bypass the limitation in CMA. You can actually go out to Excel, compute the correct effect size and variance for each study, pull it back into CMA, and now once within CMA you can go ahead and do either a fixed effect analysis on these, a random effects analysis, or anything else, any other types of procedures that you might want to do. One note, the formula for the variance, which I said before can be fairly complicated, you want to make sure that you get that right. And one way to do that would be initially at least to set the correlation to 0 or to 1, and make sure that when you do that you're getting exactly the same answers that you got in CMA. That would at least contribute to the confidence that you put the variance in there correctly. And then if you start changing the correlation, you'll be getting the correct values. In the book we do discuss at some length how that what the formula for the variance means, but you obviously want to be sure that you're getting that right. Now, up until now, all of the analysis that we were doing for math and reading assumed that we were interested in an overall academic score. We wanted to see if the treatment had an impact, and we didn't care about the difference between math and reading. Now we're going to take a different approach. We want specifically to look at the impact in math versus the impact on reading and see if those two are different. We go to run analysis. Obviously we can't do this if we are combining them into a single score. We need to click over here, select by outcome, and we're going to say use all of the outcomes, or in this case we're going to use math and reading, and treat them as though they're independent. So what we get is a row for each one of them. Then we say group by. We're going to group by outcome, and assuming that math and reading are completely independent, we get an estimate for the effect on math is 0.245 with a variance of 0.005. The effect for reading is 0.126 with a variance of 0.005. We can go to the next table. If we're going to be working with a random effects model within math and a random effects model within reading, we would be working with these numbers down here, so let's do that. In this example, it turns out that it doesn't matter whether we use a random effects model within groups or not, because the TOR square within groups is 0. But just for consistency, let's use the numbers down here. The effect size for math is 0.245, for reading it's 0.126, and the difference between them is captured by this p-value over here, which is 0.225. This is the corresponding Q statistic and degrees of freedom. Basically, this tests the hypothesis that these two effect sizes are the same in the population. Now, one thing that's very important to understand is that when we are computing an effect size across that incorporates both math and reading, the higher the correlation between math and reading, the less precise that effect size is going to be. In other words, as the correlation goes from 0 to 1, the precision goes down. By contrast, when we're looking at the difference between math and reading, which is what we're doing now, the higher the correlation, the more precise that estimate is going to be. So in other words, as the correlation goes from 0 to 1 or towards 1, that precision, that difference is going to be estimated more and more precisely. So what the program is doing over here, when we're treating these as though they are completely independent, it's assuming a correlation of 0, which means that our estimate of the precision, which is being used basically to compute this p-value, is by assuming that the correlation is 0, we're assuming basically a worst case scenario. We're making this precision as poor as it is likely to be, unless the correlation between math and reading is negative. And in that sense, this is a conservative approach. The p-value that you get is going to be higher than it should be. It's going to be closer to 1 than it probably should be. On the other hand, it is an anti-conservative approach in the sense that because you are making the p-value higher than it probably is, you are more likely to, your power is going to be lower. So just to summarize then, what we're doing over here when we are using this approach, treating them as independent, we're getting a p-value for the difference, but that p-value is probably higher than it really should be. In this case, for the sake of argument, perhaps the correct p-value would be something like 0.10 rather than 0.22. Let's see what this looks like in Excel. Finally, let's see what this looks like in Excel. The first thing that we want to do is to compute a composite score for each study, except this time the composite, instead of being the mean of math and reading, is going to be the difference between math and reading. So we're going to say the composite is equal to the math score minus the reading score. Again, we're going to need the correlation between math and reading. Let us set that initially to 0. And then we're going to need the variance of this difference. And I set this up before, and I'm simply going to copy it in over here. The formula, again, you can see it up here, is explained in the book. I want to highlight two important differences from what we did before when we were working with the mean. One is that we are no longer dividing each component of the variance by 4. The second one is that whereas before we, in computing the variance, we added a component that was based in part on the correlation, now we are subtracting a component that is based in part on the correlation. So whereas before, the higher the correlation, the larger the variance, now the higher the correlation, the smaller the variance. And that's a critically important difference as we move from the composite score to the difference score. What I can do now is we're going to, if we want to have a score for each study and then do a meta-analysis on those scores, the weight for that is going to be equal to 1 over the variance. The effect size times the variance is simply the difference. I'm sorry, the effect size times the weight is simply going to be the difference times the weight. I'm going to copy this over here to the next 4 studies. The difference then is going to be equal, I'm sorry, I need first to sum this. So the sum of the weights is going to be equal to the sum of the weights, and we get the sum of the effect size times the weight. The mean difference then is going to be equal to the sum of this divided by the sum of the weights. The variance is going to be equal to 1 divided by the sum of the weights. The standard error is going to be equal to the square root of the variance. The z-score is going to be equal to the difference divided by the standard error, and the p-value again is computed using a function in Excel. Again, the mean over here is the mean difference between math and reading. The variance reflects the precision of that difference. The z-score and the p-value are testing the null hypothesis that the difference between math and reading is 0. Let's take a look quickly to see how this compared with what we had in CMA. In CMA, when we were comparing math versus reading, we told the program to assume that they are independent. We come over here and we get an overall estimate of 0.245 versus 0.126. The program doesn't actually give us the the variance for the difference. The only thing that it gives us is the Q statistic and p-value for the difference. The difference that we're talking about, 0.245 versus 0.126, is equal to 0.245 minus 0.126, and that's a difference of 0.119, which of course is the same difference that we see over here, 0.119. The p-value that we got for this, now in this case we're dealing with 5 scores, and we're talking about the p-value for that difference was 0.22024, and in CMA it was 0.22, I'm sorry, come back here, it was 0.225024, and in CMA it's 0.225, and just to show you that there's nothing sneaky going on over here, it's 0.225024. So basically what we've done in CMA is we've done this, we've treated these things as though they're uncorrelated, and when they are uncorrelated, this is the p-value that you're going to get. We saw the same thing in Excel. If you set the correlation at 0, that's the p-value that you're going to get. We have a similar situation over here to what we had before when we were computing a composite score as the mean of math and reading, which is that we've assumed a correlation of 0, when in fact the correlation in many cases is likely to be higher than 0. If the correlation is 0, then the variance for the first study is 0.1. But if the correlation is higher, then the variance for the first study should actually be smaller than 0.1. And to show you how this works, again, I've linked each of these cells over here to this over here so that I can change all of the correlations by simply changing the value in this cell. The correlation of 0, the variance over here is 0.1. If I change that correlation to 0.5, then the variance changes from 0.1 to 0.05. When the correlation was 0, the variance over here was 0.04. If I make the correlation 0.5, that variance goes to 0.02. So the point is that if what we'd like to have is some mechanism so that we can actually put in a correlation for each of these. As we do that, we will get the correct variance, and then when we do the meta-analysis, we'll be working with the correct weights. If initially we had the variance of the difference was 0.01, assuming a correlation of 0, if we make that 0.5, then the variance is going to be 0.005. The standard error is going to be smaller. The p-value, which previously had been 0.22, now becomes 0.086. And if these correlations actually are 0.5, then these are the correct numbers down here. And when we were treating the correlation as 0, these numbers were not accurate. As before, we can use this to compute the difference score and the correct variance in Excel, and then go back to CMA and pursue the analysis over there using all of the functions that are available in CMA, including, for example, doing a random effects analysis on the differences and so on. So what we can do over here is we're going to start CMA. We're going to say insert a column for study names, insert a column for effect size data, and we will pick continuous data, hedges G, and the variance. And of course what we are actually entering over here is not hedges G, it's the difference between two, but that's not really going to have any impact on the analysis. We'll call this studies A, B, C, D, and E. The value that we're going to be putting in there we need 0.2 is the first difference, 0.1, 0.2, 0.1, and 0.1. The variance of these differences are 0.05, 0.02, 0.05, 0.01, and 0.06. And again, there's no need to have the correlation the same in each of these. We could have used a different correlation for each one. The effect direction is going to be automatic for each of them. And then when we go to run the analysis, what we're getting over here is an overall effect, an overall difference of 0.119 with a variance of 0.005. And that is exactly what we had over here, an overall difference of 0.119 with a variance of 0.005. The p-value again is testing whether the difference is 0, and that p-value is 0.086. And coming back to CMA, that p-value is 0.086. So basically what we're doing over here, again, is that we are, the effect size for each study is now the difference in that study between reading and math. The variance for each of these is correct, assuming that the correlation is actually 0.5 or whatever it was we had used for the correlation. And all of the statistics over here relate to the effect size, which in this case is a difference in effect sizes. We can check to see what happens if we use a random effects analysis. In this case, it turns out that the dispersion in differences is no larger than we would have expected by chance, and therefore the random effects model and the fixed effect model are giving us the same number. But if there had been an estimate of tau square greater than 0, then we probably would have used the random effects analysis. We can go to the next table over here, and in this case, of course, we are not dividing into males and females because each score in itself is the difference, between math and reading, because each score actually is the difference between math and reading. The point estimate we see, the standard error, the variance, and everything else corresponds to the numbers that we saw in Excel. And I hope that within a fairly short period of time we'll have all of this functionality built directly into CMA so that you don't need to go out to Excel and then come back to complete the A few final points. If you have the spreadsheet that I've been working with, down here at the bottom there's a tab for males versus females, and there's a tab for math versus reading, so that you can switch back and forth between these two different approaches to the data. I wanted to suggest again that if you're setting up these spreadsheets in Excel and you are entering the formula for the variance, be very careful that it's working correctly. One way to do that is to set the correlation to 0 and then make sure that you're getting the same answers as you would have gotten in CMA. The formulas over here, I set these up primarily for purposes of making the video. They are not general, so they're set up at the moment to work with 2 subgroups per study or 2 outcomes per study. If you're going to be working with different numbers, then you're going to need to modify the formulas accordingly, and in the book we explain how to do that. Finally, our website is metaanalysis.com. You can find information there about the program, Comprehensive Meta-Analysis, and you can use my email address, michael@metaanalysis.com, to send me any questions or comments about the video. Thanks again for your attention.